Hey guys, I wanted to do this quick code walkthrough through huff-stacker, which is a tool I wrote or I started writing a couple of days ago. The idea is pretty simple. It takes in a huff file as its input and tries to generate the stack as a comment for each macro, right? So input a huff file with a set of huff macros, output huff file with a set of commented macros, and the comment is basically the stack history, right? So yeah, let's take a look at the implementation. So the entry point is main. Which it has a pretty simple interface, I think. It takes in a path to the file and an out path where it puts in the commented macros, right? So it creates a new file. Ideally, if you wanna put that into Vim or VS Code, it actually puts that into the original Huff file. But that's very easy to do. You would basically do this, right? So pass in is pass out. All right. So the first thing it does is parse. So let's take a look at parser. So in parse, the parse function inside parser basically parses out each macro from the huff file, right? And so inside the code base, I always call a macro a function because a macro is a Rust keyword. So yeah, I just called it a function. So yeah, let's take a look at the function and the properties it has. So a function has a name, a start. Okay, let's actually take a look at an example macro. So a function has a name. In this case, it would be set value to. A start, which is the line number it starts on, an end, which is the line number it ends on. Takes is the number of arguments the function takes from the stack. Returns is the number of arguments it puts on the stack after it finishes or returns. The body is the body of the function or the macro. And where it gets interesting is the stack history. So let's look at stack history. So stack history is defined by a list of stacks, and a stack is a list of tokens, right? Why do we need the stack history? Because to print out the stack comments, you have to know the state of each stack in time, right? So I basically generate for each line, I simulate what the opcode does. In this case, it pushes a 0x04 onto the stack. But I need to remember that. And this is why I have the stack history. So I go through each opcode, 0x04 does the same again, pushes 0x04. XXYY is actually another macro which it calls into, which takes in one argument and returns one argument. This is what I try to symbolize by percentage 0. If it would return 2, it would have XXXYYY percentage 0 and XXXYY percentage 1, right? Yeah, and this is basically how it does that through a stack history. Okay, let's jump back into the parser and look at how the parsing actually works. Okay, so we have a function which is called parse function, right? And parse function takes in the contents, basically the whole file, and the skip parameter. So when you find a function, it remembers that, And the next time you call into parse function, you put in a skip to skip that function you just parsed. And this is how you jump from one function, so from one macro to another. Okay. Okay. So yeah, we basically iterate over every line and check for a macro start. So macro start is basically this, the define macro, right? And we check, does the trimmed line, so we obviously trim the line to remove white spaces and stuff. We want to trim the line and check for if it starts with the macro start. Then we save the function start. Parse function name, it's just a simple regex which parses out the macro name, right? Parse function args is basically the same. It's another regex which returns the takes and the returns, and we save those, right? So now we have the start of the function. End of the function is pretty similar. We just check for, does the jump line start with a macro end? Macro end is this. So closing curly brackets, and yeah, we set in function, so we remember that we are inside the function. And here we set it to false because we're at the end of the function, and the rest is basically the body, right? So we parsed out the function, the start, the end, the name, takes, returns, and the body. And once we have a function, we still have to do some things, right? So this is why it's mutable. Okay, skip is to go through to another function, but this is not the interesting part. So we generate jump labels. This is actually a feature which isn't implemented yet because it's the hardest thing actually to simulate jumps, because you actually not only have a stack history through the possible jumps, which is a big feature that's still missing, but we are generating the jump labels. So for example, we generate out the success jump label here, for example, right? Then we push it into the functions vector, functions list, and we push it into a functions map, which is also interesting, I think. What is a functions map? So the functions map is a hash map, or a mapping from the name of the function to the function struct. And we need that in order, when we are generating the stack history, we need that to get the argument it takes and returns for a specific macro. So for example, this here, I need to know what the xxxyy function macro takes in and returns. And this is why we have this functions map, so I can, while I'm generating the stack history, I can index it by its name and get the information that I need. Okay. What we also do here is when we initialize the function map, we put in the built-in function that Huff provides. So for example, function signature, event hash, write pad, and so on, and all these functions. So we have a built-in function here. All these functions take one thing of the stack and pushes another on the stack. Right. Okay. So yeah, that's the function map. Okay. The most interesting thing now is, once we have initialized the functions map, and parsed out the functions, we actually need to generate the stack history, which happens here. So let's go into gen stack history. Okay. This is where the fun begins. It generates the stack history for one function, and it also has access to the function map. Actually, looking at this, I think it would be good refactor, maybe a first PR for someone who wants to contribute to push that, to add this function map to the function struct. No, it's not a good idea. But there is a cleaner way than to always having to add this function map to the gen stack history call, I think. Okay. All right. So we initialize the stack history, and we initialize a new stack, and we check if the function takes arguments. So we have something called push takes inside the stack, and the push takes basically checks, okay, if I take more than 0 arguments, I push these constants onto the stack. So basically I push these, so this function takes 2, it pushes $0, $1 onto the stack. Right. So we do that to initialize the first stack. And then we basically iterate over the body of the function. So for each line in the body, if the line, we trim the line and check does it, if it starts, if it is a comment, // we just ignore it. If it's not, we get all the tokens on the line. So one thing the huff-stacker supports is multiple opcodes per line. And how it does that is through the parse line function call here, which, if we take a look at parse line, takes in a line, it splits it by white space, and it creates a list of tokens, and it calls into token from string, which basically looks at this. If it starts with 0x, if it starts with a constant start, it's a constant. If it's a reference, if it's a variable, if it's a function start, so function start would start with an underscore. If it's a jump label, and if it's none of these, it's an opcode, right? So it sets a token type here, and it sets a token value. So basically it creates these tokens, and if we look at the token struct, it has a value, it has a type, it has an optional opcode. Not every token is an opcode, and it has a set of operands. Right. Okay. Good. All right. So it pushes that onto the tokens and returns this. So if we go back into the function and look at the stack history, general stack history, it returns a list of tokens, and then it iterates over each token. So for each line on the function body, for each token on the line, we have to do something. Let's close this for a second. So if it's a constant, a reference, or a variable, we just push it on the stack. If it's a function, we execute that function. If it's an opcode, we execute the opcode. So in the stack, we have, let's look at execute function first. So we check how many parameters it takes from the stack. and we pop those. And this is, by the way, where we need the functions map, right? Because we index into that to get the function that actually executes. And for each parameter it returns, we create this return token type, which when we output that, it's actually this thing, right? So that's execute function. For the opcode, we actually want to save the operands. So yeah, important. We need to set the operands before executing the opcode, because we want to take these operands from the stack, right? So if we execute opcode, we look at one opcode and see how many it pops, and how many it pushes. So in this case, each opcode, which are defined here, there's no opcode in the EVM which pushes more than one. So it's either doesn't push anything or it pushes one. This is why we only check for equals one. Okay. So once we do that, so these are operations on the stack, right? Stack push, stack execute function. So we do operations on the stack for each line. We push that into the stack history. So for each line we have one stack, and we return that. And this is how we generate the stack history. So after doing this, we basically have something we can print, or we can create the comments with. So if we go back into main, there is a write function which takes a path in, a path out, and a list of functions. And remember, each function has its stack history. And the write function is defined in printer. And so printer reads in the file again, creates a list of strings for the file, which is content lines, and then it iterates over every function and creates the comments for each function. So it's basically, after create comments, it's basically the body plus the comments. No, that's actually not correct. So if we look at create comments, it's actually only the comment. So it would be this, only this. So when we have that for each line, we actually call merge, and merge is where we merge the initial line, the initial opcodes with the comments. And this creates the content lines for each function. And in the end, we iterate over each line in the content lines to create the final output text. And this is what we write into the new file, or the old file, whichever one you prefer. For debugging, I just always create a new file, so I don't overwrite the old one. Alright, so yeah, in the merge function, it's not super interesting. We just check is it a comment or an empty line, for example. So this is an empty line, we don't need to print out the stack. Actually, internally there is a stack comment here. So it basically has this stack comment also here, which it was just an easier way to implement the stack history function. But obviously when we print that, we don't want to print that for an empty line or for a comment actually. Yeah. So okay, this is also interesting, I think. What we also do is we check for stop, which is the stop opcode. And I think there is not an example here actually. So, okay, so if we have a stop opcode here, and we do a run, and we look at the output, it just stops here, right? So it encounters the stop opcode, and it says, okay, we don't need to put in the rest of the comments because there's no way to reach that, and we also put in this little end label here. Okay. Yeah, so I think that's it. The code is on GitHub under sha0x/huff-stacker. If you want to refactor stuff, please feel free to do so. We actually have an open PR right now for refactoring some things, which is great. But also, if you wanna start working on the jump logic, that would be really awesome. As I said before, I started some work implementing that. So there's a jump labels map, which, if you look at that, it's basically a mapping between a jump label name and the jump struct. So jump label struct has a name and where it starts. Nothing fancy right now, but one can definitely build on this. So yeah, that's basically it. Thanks for tuning in, and yeah, looking forward to your PR or contribution or something. It would be awesome. All right.